We've seen that we can use basic trigonometry, sine, cosine, and tangent, to work with right triangles, but we haven't applied trigonometry to triangles that are not right triangles. So let's take a look at the triangle given here. We have triangle ABC. It's definitely not a right triangle. We're given angle A is 60 degrees and angle B as 50 degrees. Side B, remember the convention for labeling. The uppercase letters are for the vertices or the angles. The lowercase letters are for the sides. And the side B is always opposite angle B. So in this case, lowercase b is 10. That means side B is 10. And we're looking for lowercase a. In other words, we're looking for the length of side A. So initially it looks like we can't apply basic trigonometry, but we can actually turn this into a right triangle problem just by drawing a perpendicular line to side C, and we can call that point of intersection point D. So now we have two right triangles, and we can certainly use trig on the left-hand side to find that altitude. CD is called an altitude. So let's see what we would do. If we were looking at the left-hand triangle, we could say the sine of 60 degrees is equal to the opposite over hypotenuse, which is CD over 10. And we can multiply both sides by 10 to get 10 sine 60 equal to CD. Now, if we know what CD is, and we can plug that into the calculator very easily, we can work with the triangle on the right, because we know angle B, and we now know the side opposite angle B in the right triangle BCD, and we're looking for the hypotenuse. So once again, we can use sine. We can say sine of 50 degrees is equal to the opposite, which in this case is CD over A. And we know what CD is. A is what we're looking for, so we've got to do a little extra work to solve for A here. We can multiply both sides by A. So A sine 50 is equal to CD, and then divide both sides by sine 50, and we get A equal to CD over sine 50. And what is CD? Well, it's 10 sine 60, or you could punch it into the calculator first. But it's nice to leave it as 10 sine 60 over sine 50. And then, of course, at this point, if you want to go any further, you would have to reach for your calculator and plug that in. And if you want to round it to the nearest tenth, you would get approximately 11.3. So, in a way, we could sort of do this without numbers and create a formula for finding all the missing sides. Just like using the parameters a, b, and c in a quadratic equation, ax squared plus bx plus c, and then solving that quadratic equation sort of once and for all and creating a formula called the quadratic formula. Well, that's exactly what we're going to do. So let's start with the same sort of triangle. Instead, in this case, though, we're just going to label it A, and we'll assume that we've been given angle A. B, again, we'll assume we've been given angle B. C, side B, again, is given, and we're looking for side A. So what were the steps we did? Well, we created two right triangles by drawing in this altitude and labeling that point D. Then we worked with the right triangle on the left, and we said the sine of angle A was equal to the opposite, CD, over the hypotenuse, B. And we multiplied both sides by B to get an expression for CD. Then, working with the right triangle on the right, we said the sine of angle B was equal to the opposite over the hypotenuse. And we multiplied both sides by A, and then divided both sides by sine B to get an expression for A. CD over sine B, and we knew what CD was. It's this thing over on the left, B sine A. And there we have our formula for side A. It's B sine A over sine B. And we could do this for all the sides of the triangle. But if we just do one little manipulation, we can get a much more elegant formula that will be very easy to remember and very easy to work with. If you can imagine taking this expression here, A equal to b sine A over sine B, and just simply dividing both sides by sine A, we get A divided by sine A equal to B divided by sine B. And that encapsulates a relationship we've known for quite a while, which is that when you are looking at a triangle, the side opposite a bigger angle is going to be bigger. Now, it's not a linear relationship, but we know for sure that if we have a bigger angle, the side opposite that bigger angle is going to be bigger. And this expression right here tells us exactly how much bigger. As you increase the angle, the sine of the angle increases, and therefore the side opposite must increase. There's this ratio that we could actually calculate for any given triangle, which is the ratio of a side to the sine of the angle opposite it, and it's going to be constant for any given triangle. Now, we could just relabel this triangle and do this all over again and get a third relationship here, which is that C over sine C is equal to B over sine B, or A over sine A, depending on which way we did it. And this whole expression is known as the sine law. And it's very easy to remember. A over sine A equals B over sine B equals C over sine C. We can rewrite it as the reciprocals equal to one another too. We could write it as sine of angle A over lowercase a is equal to the sine of angle B over lowercase b is equal to the sine of angle C over lowercase c. And both are fine. It just depends on what you're looking for. If you are looking for a side, you always want to have that unknown in the numerator, and so you're going to want to use the relationship on the left. If you're looking for an angle, again, you always want to have the unknown in the numerator. It just makes computation a little bit easier, and so you're going to want to have one of the expressions on the right. So we can use this to find missing sides, but we can also use it to find missing angles. So let's try a couple of problems to see how we would actually apply it. Let's say we are given a triangle, and I'll say it's triangle ABC once again. This time, let's say we're given angle B is 48 degrees, and angle C is 70 degrees. Sometimes you're just asked to solve a triangle, which means find all missing sides and all missing angles. So if you're given two angles, it's very easy to find the third. You just have to subtract from 180. But let's say in this particular case, we're given one of the sides, 35. That's side C. And we're looking for side B. Now, one of the things you have to learn is when you can apply the sine law. I always like to say that you need a matching pair. You need to have an angle and the side opposite the angle, because you need that ratio. That ratio is constant in a given triangle. If you don't know what that ratio is, you can't apply the sine law. So if you're looking at this triangle and making the decision as to whether you can apply the sine law, you want to see that matching pair. And we have it here. We have angle C and side C. So we can use the sine law. And when I set up the sine law, again, I always start with my unknown. My unknown in this case is side B. So I put that first, and I put that as my numerator. The denominator will be the sine of angle B, which in this case is 48 degrees. And then since I started with a side as the numerator, I need to have another side as the numerator. That'll be side C, which is 35. And the denominator will be the sine of angle C, which is 70. So I now have an equation where there's just one unknown, and I can solve that quite easily by multiplying both sides by sine 48. And I get B equal to 35 sine 48 over sine 70. And at this point, I just punch that into my calculator, and I get approximately 27.7. And again, if you look at your triangle, were you expecting side B to be less than 35 or greater than 35? Well, it's opposite an angle that's only 48 degrees. It's smaller than 70 degrees. So you should have been expecting a side smaller than 35, and sure enough, we got one, 27.7. So that's a good habit to get into. Now, we can also use the sine law to find missing angles, but we are going to run into a problem, and that problem we started essentially exploring in the last video when we were trying to construct different triangles given certain information. So let's say we have a problem where we are given an angle and two sides. So let's say we are given angle A is 30 degrees, side A is 15, and side B is 22, and we're looking for angle B. So we don't have a diagram to work with. We have to draw our own diagram. So let's draw the 30-degree angle first. I don't really know how long this base side is, but I do know this is, let's say, 30 degrees. So there's my 30 degrees. And B is somewhere along here, but exactly where I don't really know. This is side B, though, and that's 22. And so the third side is up here, C, and that's fixed. Now, side A is 15, and I can certainly draw it in like this. And I can make that my B. And I don't really need the rest of this, but I'm just going to leave it dotted so that it hopefully will bring back some memories of the last video for you. And now I can go to work trying to find angle B. So I can set up using the sine law. I can say sine B over side B, which is 22, is equal to sine 30 over side opposite the 30-degree angle, which is 15. And I can multiply both sides by 22 to get sine B is equal to 22 sine 30 over 15. Now, sine 30, I've chosen 30 because sine of 30 is a nice number. It's a half. So I can simplify this to 22 times a half, which is just 11 over 15. Now, if I know what the sine of an angle is, I can use arcsine to find the angle. So I can say B is just equal to arcsine of 11 over 15. And I can punch that into my calculator, and I can get an angle. Turns out to be 47.2 degrees. So this angle is 47.2 degrees. End of story. Well, maybe not quite. As you saw in the last video, the diagram I drew here is not the only diagram that will satisfy the given information. That side length 15 could just as easily be over here on the left. That would work. It would generate a triangle. And instead of the B being over there on the right, the B would be over here. And you can see from the triangle I've just constructed, it's isosceles, which means that the 47.2 degrees I found is going to be the same right there, which means that this angle B, this new angle B, is supplementary to 47.2, meaning that the two angles add to 180. So it's 180 minus 47.2, which is 132.8 degrees. So in fact, there are two possibilities for B. B could be 47.2 degrees, but it also could be 132.8 degrees, because there are two different triangles I can construct. One is obtuse, and one is acute. The obtuse triangle has that big angle, 132.8 degrees. The acute triangle has the 47.2 degrees. Now, of course, these two different triangles would also lead to two different angle C's and two different side C's. And so you've got to work perhaps with two separate diagrams if you want to solve this triangle and figure out all the sides and angles. Now, we've encountered this problem before where we had two different angles when we had the sine of an angle equal to a particular number. So earlier in the chapter, if you recall, when you were given an equation like the following, sine of b equal to 11 over 15, and you were told that b could be anything between 0 and 360 degrees, well, how did you solve this problem? Well, my suggestion was the first thing you would do would be to draw a unit circle and then think about what sine means with respect to a unit circle. Sine means y. And so really what we're looking for is where on the unit circle is there a y value of 11 over 15. Well, 11 over 15 is about 2/3, so it's about 2/3 from the origin up to the top of the circle. If you draw in that line, y equal to 11 over 15, you can see that it intersects the circle in two places, which means there are two different values that give you the right sine ratio. We've got one there and one there. Now our calculator will only ever tell us one of those. So when you punch in arc sine of 11 over 15, you get what we got above, which is 47.2 degrees, which means that this angle here is 47.2 degrees, and we can refer to the point up here in quadrant 1 as 47.2. But by the symmetry, we have a 47.2 degree reference angle over here in quadrant 2. So if we want to actually calculate that angle, we have to think of it as 180 minus 47.2 degrees, which is 132.8. And so when you saw this problem before, you solved it by creating this diagram and then realizing that we have two different places on the circle that have a given y value, and those two places correspond to angles in standard position of 47.2 degrees and 132.8 degrees. And you can check on your calculator. You take the sine of 47.2, the sine of 132.8, and they're going to be identical, and both almost exactly 11 over 5. Bit of a rounding error. Now, you don't always have to worry about the ambiguous case. If you go back and look at the previous video, you'll see that there are certain conditions under which we have to worry about the ambiguous case. There are many situations where you use the sine law to solve for a missing angle, and there's never any doubt that you're looking for one and only one angle. All right, so it will take a little bit of experience. You have to play around with some different triangles to realize when you can be sure and when you can't be sure. In general, if you're looking for an angle that's opposite a side smaller than the other side given in the triangle, then you don't really have to worry too much because you know your angle is going to be smaller than the other angle. But when in this case we were looking for angle B, which was opposite a 22, a length 22, and so we knew we were going to get an angle bigger than 30, but how much bigger than 30? We don't know. We don't know whether it's actually going to be bigger than 90, which is possible in this example.